Hi, my name is Theertha. I'll be talking about learning discrete distributions, user versus item level differential privacy. This is joint work with Yuhan Liu, who is a PhD student at Cornell, and Felix, Sanjeev, and Michael, and we are at Google Research. Here is an overview of the talk. I'll start with some basic definitions of differential privacy, and I'm going to highlight two important versions of it, which are item level and user level privacy. Then we are going to look at the problem of learning discrete distributions and analyze few standard approaches. We then propose a new polynomial time algorithm and show that it is also information theoretically optimal. So let's start with the definition of differential privacy. Let calligraphic M be a mechanism or an algorithm. You can think of this as an algorithm to learn neural networks or parameters of a distribution. We call a mechanism M epsilon delta differentially private if for any two neighboring data sets D and D prime, the probability that they output something differ at most by a multiplicative factor of e to the epsilon and an additive factor of delta. I won't go too much into the details of this definition, but I would like to point out that the notion of differential privacy we are studying is called global differential privacy. Here, the goal is to just ensure the output of mechanism M to be differentially private. And it's not to privatize the entire data set itself. For example, if you learn a discrete distribution, the goal is to ensure the learned distribution is differentially private. If you learn a neural network, the goal is to ensure that the parameters of the neural network are differentially private. To implement it, typically one needs a trustworthy central server, but you can also do it without a server by using some cryptographic primitives, and I won't go into details of it. Now let's go back to the definition of differential privacy. I've highlighted here neighboring data sets. So the question is, what are neighboring data sets in differential privacy? Typically, in differential privacy literature, two data sets are considered neighbors if they differ in one item. For example, here you have two data sets, D and D prime, both consisting of data from 4 users. They have exactly the same data except in user 4, where in one case it's SSN and in the other case it's the word I. This we call item level privacy because, loosely speaking, the goal is to protect the privacy of an individual item. However, in practice, users typically have many examples. For example, think of data from a mobile keyboard where you want to count the distribution of words. Some users may type just one word, some users may type hundreds, and some may even go up to thousands of words. This is a very common scenario in federated learning where the number of samples from each user is very different. If you naively apply item level privacy, then it just protects the privacy of a single item and does not protect the privacy of all the items of a user. I'm hand waving here, but this can be formalized. To overcome this, researchers have resorted to user level privacy, where two data sets are considered neighbors if they differ in the data of one user. For example, here, data sets D and D prime have same data from first 3 users, but for user 4, the samples they contain are completely different. Since here the goal is not to just to protect the privacy of a single item, but to protect the privacy of an entire data of a single user. A natural question is to understand the utility privacy trade-offs between user level and item level privacy. Loosely speaking, in user level privacy, since we are trying to protect the privacy of entire data set of a user, it's much harder to do, and you need to incur a lot more privacy penalty compared to item level privacy. And our goal is to understand this precise trade-off. To do this, we are going to look at a well-defined statistical problem. We are going to consider the problem of estimating discrete distributions. To be more concrete, let P be an unknown discrete distribution over K symbols. You can think of it as distribution over words. And we have S users. And just for the purposes of this talk, I'm going to assume each user has exactly M samples. In general, M need not be 1. And I would like to note that we extend it to the scenario when users have different number of samples, but I won't go into details in this talk. Our goal is to understand the user complexity, that is, how many users do we need to learn P to a total variation distance of alpha. So just to recap, we have 4 parameters. P is the unknown distribution, S is the number of users, M is the number of samples per user, and alpha is our target total variation distance. Let's start with item level privacy, the simple case when every user has 1 sample each. A typical algorithm looks as follows. You first compute the count of each symbol, and then you normalize it to get a probability. And then you add some appropriate Laplace or Gaussian noise to ensure differential privacy. For example, here I have a data set with 4 users, and if we are interested in probability of the word hi, we find a count of hi, which is 2. We divide it by total number of samples, which is 4, and we add some Laplace noise. And we need to do some post-processing to ensure there is a valid probability distribution, but for the purposes of this talk, it's not important. So one can analyze this mechanism to see how many users do we need to get a total variation distance of alpha to the underlying distribution. And that's here in the bottom of this page. It's k divided by alpha square plus k by alpha epsilon. Recall that k is the number of symbols, alpha is the total variation distance, and epsilon is the privacy parameter. The first part, k by alpha square, is the statistical complexity. It's the number of users you need, whether you care about differential privacy or not. The second part is the privacy complexity, which goes to infinity if you require more and more privacy. So it scales with privacy parameter epsilon as 1 by epsilon. So this trade-off is known to be optimal, and many mechanisms such as Gaussian mechanism or exponential mechanism would have similar user complexity. Let's first try to understand what happens if we just apply this type of algorithms for user level privacy. Recall that each user now has M samples. So as before, we compute the count of each symbol and we add appropriate Laplace noise. This requires a little bit of math, but the amount of noise you add depends on what's called sensitivity. And the sensitivity here turns out to be 1 by S, where S is the number of users. So again, if we can compute the probability of hi as count of hi divided by total number of samples, which is S times M, plus some Laplace noise. We can again analyze this. And it turns out the number of users necessary would be k divided by M alpha squares plus k by alpha epsilon. Similar to the previous slide, we have a statistical complexity and a privacy complexity. The statistical complexity, highlighted in blue, goes to 0 as 1 by M, meaning if you have more samples per user, then you need fewer number of users. However, somewhat surprisingly, the privacy complexity is independent of M, meaning irrespective of how many users you have, the number of how many samples per user you have, you need a lot of users. And this was really the starting point of our work. We were surprised to see that privacy complexity does not go down as a function of M. One can look at several other algorithms like Gaussian mechanism or some subsampling approaches, and we notice that all of them have the same user complexity. The privacy complexity is fixed and does not go to zero as a function of M. So we analyzed it a bit more, and we could actually prove an information-theoretic lower bound, which takes for a broad class of, I'm calling it standard epsilon delta differentially private algorithms, the privacy complexity is independent of M. In fact, it's k by alpha epsilon, which is same as that of the privacy complexity of item level privacy. This was very surprising for us. So we investigated further and we proposed a new algorithm. I'll come to the details in a bit, but our main result is as follows. We propose a new polynomial time epsilon delta algorithm such that the privacy complexity goes to zero as 1 over square root m. And we also show that this is near optimal by proving an information-theoretic lower bound. For any epsilon 0 algorithm, one incurs a privacy penalty of k divided by square root m alpha epsilon. Let's summarize all the results. So if one is interested in just item level privacy, where m equals 1, the number of users necessary is k by alpha square plus k by alpha epsilon. If you use many existing standard mechanisms, then the statistical complexity in fact goes down as k by m alpha square, but the privacy complexity does not change with m. Our main contribution is to show that the privacy complexity scales as 1 over square root m, and further, it's optimal. In the remaining time, I'm going to briefly go over our proof ideas. For the lower bound, we use a differentially private version of Fanos and Answar's inequality. And the proof mainly requires on coupling arguments. This was recently studied by a paper by Acharya et al. Our main contribution here is to extend this notion to a class of restricted estimators, which do not perform on the actual statistics, but a function of the statistics. We need this to prove lower bounds for the standard Laplace and Gaussian algorithms. Let me move on to the algorithms. Our main observations are as follows. We first consider two cases, sparse regime and dense regime. In the sparse regime, we only look at symbols whose probabilities are small. Say p of x is less than 1 by m. Since each user has m samples, typically most symbols appear either 0 or 1s per user in this regime. The second regime we look at is a dense regime, where symbols have probability bigger than 1 by m. Here, the symbols appear many times. In the sparse regime, our main observation is that symbols appear either 0 or 1s most of the times. So instead of aggregating the counts like we did for Laplace or Gaussian mechanism, we propose to count how many users have a particular symbol or not, and sum up the number of users who have, whether they have a symbol or not. We show that this reduces the sensitivity, and hence the algorithm has better utility. Dense regime is more challenging because each symbol can now appear many, many times. In fact, it can appear as large as m times. To understand our main intuition, it suffices to consider k equals 2 when you have only two symbols, say Bernoulli P. Our main observation is the following. Estimating a Bernoulli P with user-level privacy is same as estimating a binomial m comma p with item-level privacy. This is because if each user has m samples from a Bernoulli distribution, it's same as having one sample from a binomial distribution. Once we have this observation, we can estimate the density of a binomial distribution using differentially private Sheffer algorithm. And we then infer the underlying Bernoulli parameter p by using the density of binomial m comma p. And to do this, we propose a new bounds on total variation distance between binomial distributions in terms of their parameters. So that's a brief overview of an algorithm. If you're more interested, please look at our archive paper. To summarize, we started this theoretical analysis of user-level differential privacy, and we focused on learning discrete distributions. We proposed a polynomial time algorithm and matching information theoretic lower bounds. Thank you.